What if one of the most famous theories in modern science is not actually science at all? For decades, string theory has been presented as the final key, the hidden code, the elegant bridge between Einstein's universe and the quantum world beneath it. It promised something almost mythical, one equation that could explain everything: the birth of time, the force of gravity, the dance of particles, the shape of reality itself. And for a while, many believed that physics was standing at the edge of its greatest revolution. But behind the polished documentaries, the best-selling books, the standing ovations, another story was quietly unfolding, a story filled with doubt, because some of the most brilliant minds alive began asking a dangerous question. What if string theory is beautiful, but wrong? And that question became impossible to ignore. To understand why, you have to go back to the moment physics itself split in two. In the early 20th century, science discovered something deeply unsettling. The universe seemed to follow two completely different rule books. On one side, there was Einstein's relativity, the universe of smooth space and time, a cosmos where gravity bends the fabric of reality like a heavy ball sinking into a stretched sheet. It explained planets, stars, galaxies, black holes. It described the large. But then came quantum mechanics, and quantum mechanics described the small, not with certainty, but with probability, particles that behaved like waves, objects that could exist in many states at once, events that seemed random at the deepest level. It was as if nature itself had two personalities, one calm, one chaotic. And the terrifying part was this: both theories worked perfectly. Each one predicted reality with astonishing accuracy. Yet when scientists tried to combine them, the equations collapsed into nonsense, infinity, contradiction, mathematical disaster. Physics had reached a wall. And for generations, scientists searched for a way through. Then string theory appeared. At first it sounded almost absurd. What if particles were not particles at all? What if the tiny points we call electrons and quarks were actually unimaginably small vibrating strings, tiny loops of energy, smaller than anything we could ever directly see, each vibration creating what we experience as matter? One vibration becomes an electron, another becomes a photon, another becomes a quark. Like notes on a violin, different vibrations, different realities, and suddenly, for the first time, the impossible seemed possible, because in those equations, gravity appeared naturally. That was the miracle. For decades, gravity had refused to fit inside quantum mechanics, but in string theory, gravity seemed to emerge by itself. To many physicists, this felt like destiny. Not just a theory, a revelation. Brian Greene became one of its most passionate voices. To him, string theory was more than mathematics. It was a glimpse behind the curtain, a framework where all forces could be united, where nature's complexity could be reduced to one underlying principle, where the chaos of the universe might finally reveal a hidden harmony. And people listened, because Greene spoke about string theory the way poets speak about truth, not as dry equations, but as a vision, a universe made of music, invisible symphonies vibrating beneath everything we know. And for a public hungry for wonder, it was irresistible. But here's where it gets strange. The more beautiful the theory became, the harder it was to test. Real physics has always lived by one brutal rule: a theory must risk being wrong. That is what separates science from philosophy, from belief, from imagination. A scientific theory must make predictions, and those predictions must face reality. If reality says no, the theory dies. That is how science moves forward. But string theory never seemed to face that moment. Because the strings were so small, no machine on Earth could observe them, no experiment could confirm them, no telescope could see them, and every time the theory failed to match reality, the mathematics seemed flexible enough to adjust. A new dimension could be added, a hidden symmetry could be proposed, another layer could be invented. Instead of becoming sharper, the theory became larger and more slippery, and that began to trouble people, not outsiders, not amateurs. Some of the most respected physicists in the world. Roger Penrose was one of them. Penrose was not just another critic, he was one of the greatest mathematical physicists of the modern era, a man whose ideas reshaped our understanding of black holes, space-time, and consciousness itself. Roger Penrose saw something deeply unsettling in string theory. He believed physics was drifting away from reality, because to him, elegance was not enough. A theory could be beautiful, A theory could be sophisticated. A theory could even be mathematically dazzling and still be wrong. Penrose warned that physics was becoming seduced by aesthetic beauty, that some scientists had begun trusting elegance more than evidence, and history had seen this before. Sometimes the most dangerous ideas are not ugly. They are beautiful, because beauty can make people believe before proof arrives, and string theory was almost too beautiful. But that is only half the story, because the deeper physicists looked, the stranger the problem became. String theory did not produce one possible universe. It produced something far more disturbing. It produced millions, then billions, then numbers so large they barely felt real. Possible universes, possible laws, possible constants, possible realities, a landscape of mathematical worlds. Some estimates suggested there could be 10 circumflex 500 different solutions. That is a 1 followed by 500 zeros, a number so vast it no longer feels physical. And suddenly the dream of one final theory began to fracture. Because if a theory can predict almost any universe, does it really predict anything at all? That question began to haunt the field. Because science depends on exclusion, a theory must tell us not only what can happen, but what cannot. And string theory seemed willing to allow almost everything. That meant the theory could bend around observation instead of confronting it. And that raises a bigger question. If a theory can never fail, is it still science? That question did not stay in quiet academic halls. It started spreading from conference rooms to university departments to private conversations between physicists who had spent their lives searching for truth, and eventually some of them said the quiet part out loud. Eric Weinstein was one of the loudest voices to challenge the culture around it. Eric Weinstein, his criticism was not only about equations, it was about power. He argued that modern theoretical physics had created something dangerous. A system where prestige could protect ideas from scrutiny, where careers could be built on promises that never had to be fulfilled, where questioning the dominant framework could quietly cost a young scientist everything. Because science is supposed to reward doubt, but sometimes institutions reward loyalty, and Weinstein believed string theory had become more than a theory. It had become a kind of intellectual empire, a place where mathematical sophistication could hide a deeper problem, no contact with nature, and this was uncomfortable, because the people defending string theory were not frauds, they were brilliant. Brian Greene was not misleading people. He genuinely believed the theory pointed towards something profound. Brian Greene, many of the physicists working in the field were sincere, disciplined, deeply intelligent. That is what made the story so unsettling, because sometimes the smartest people in the world can still become trapped by an idea. Not because they are foolish, but because intelligence can make a beautiful idea even harder to let go. A simple mistake can be abandoned. A magnificent mistake can survive for decades, and this is where everything changes. The real argument was never just about strings. It was about what physics is supposed to be. For centuries, physics earned its authority in a brutally simple way. It touched reality. Galileo dropped objects. Newton explained motion. Einstein predicted light bending around the sun. Quantum mechanics predicted particles with absurd precision. Nature always had the final vote. That was the sacred rule. No matter how elegant your theory was, reality could still say no. But string theory seemed to live in a different world, a world where mathematics itself became the evidence, and that created a philosophical divide inside science. Some physicists believed mathematics reveals reality, that if the equations are deep enough, nature must eventually follow. Others believed mathematics is only a language, a tool, and no matter how beautiful the language becomes, it cannot replace experiment. Penrose stood closer to that second camp. He never denied that mathematics matters. He understood mathematics better than almost anyone alive, but he believed beauty should guide physics, not replace it. That distinction changed everything. Because once a field stops needing experimental confirmation, it enters dangerous territory. It can slowly drift from physics into metaphysics, from discovery into speculation, from science into belief. But scientists found something even more disturbing. String theory was not merely unproven. Some critics argued it had slowed physics itself. For years, enormous talent flowed into one direction. Graduate students spent entire careers mastering equations that might never connect to experiment. Funding followed prestige. Departments followed trends. Alternative ideas struggled to survive. And in science, attention is not free. When one idea dominates for too long, other possibilities can disappear in the shadows. No one knows how many discoveries may have been delayed because an entire generation chased the same mirage. That possibility is hard to measure, and even harder to admit, because science likes to imagine itself as purely objective. But science is still done by human beings with reputations, with ambition, with fear, with hope, and sometimes those forces shape knowledge more than anyone wants to admit. That does not mean string theory is false, and that is the uncomfortable part. No one has proven it wrong. Not completely. It could still contain something real, some fragment of a deeper truth we do not yet understand. Some mathematical shadow of a future theory still waiting to be born. That is why the debate refuses to die, because string theory lives in a strange place, too sophisticated to dismiss, too untestable to confirm, too influential to ignore. It sits in a grey zone between genius and illusion, and maybe that is why people cannot stop talking about it. Because at its core, the argument is not really about strings, it is about the line between imagination and reality. How far can science go before it stops being science? How much beauty should we trust? How much mystery can physics tolerate before it becomes philosophy wearing equations? Those questions are bigger than one theory. They cut to the heart of how humans search for truth, because every generation faces the same temptation, to confuse elegance with certainty, to mistake complexity for depth, to believe that a beautiful idea must somehow be true. But the universe has never promised to be beautiful in ways we can understand. Sometimes reality is elegant. Sometimes it is brutal. Sometimes it refuses to care what we want. And that may be the hardest lesson in all of science. The universe does not reward the most beautiful theory. It only rewards the one that survives contact with reality.